Here is a modelling paper called Drilling a Tunnel from June 2013. On the plan, A is south of B, so there's A directly underneath B, and C is east of B, so here we go, east. AB is 500 metres, as can be seen from the diagram, and BC is 300 metres. It says it's not drawn to scale. Engineers want to drill a tunnel from A to C. The tunnel has one or more straight sections. So what that means is that every bit of the tunnel is a straight line, but it could be more than one straight line. So what you can't do is something like a curvy tunnel like this to get from A to C. Calculate the length of the shortest possible tunnel from A to C. Give your answer correct to the nearest meter. Well, the shortest distance between 2 points will always be the straight line, so let's draw that. And because we are told that this is east and this is south, that means that they are perpendicular lines. So we have a right-angled triangle. We know two sides and we want to know the other one. So if we just call this X or D or L or even AC, probably be better. This is Pythagoras' theorem. We have a right-angled triangle. We have two sides. We need the third one. We are looking for the long side opposite the right angle. So it must be small side squared plus small side squared equals big side squared. So 300 squared plus 500 squared equals AC squared. That must mean that AC squared equals, just go to the calculator, 300 squared plus 500 squared. Okay, we just go to our calculator, 300 squared plus 500 squared. That gives us 340,000. So AC must equal the square root of that. Square root of the answer. And that gives us 583.095. So if we just go to three significant figures, that is 583 meters. And it actually asked it to the nearest meter anyway. Write down the length of tunnel if the engineers drill through as little hard rock as possible. So now if we look at this, you can see everything unshaded. The white bits are normal rock, and this shaded area, the dark area, is hard rock. So remember, the tunnel can only be straight sections. The way to drill through as little hard rock as possible, well, that's going to be if we go through the normal rock all the way here. So the smallest amount of hard rock will be here at 300. You can see, looking at this map, you're never going to get a shorter distance through hard rock. You've got to go through some hard rock than here, because if you look at this borderline here, it's always getting wider. Or here it narrows a bit, but it certainly doesn't go narrower than that. So I think we need to go 500 meters through normal rock from A to B, and then we need to go 300 from B to C. So it's going to be 500 plus 300, and that gives us 800 meters. Point P, or P, is a point X meters south of B. So we have a general point P. So already they're just bringing in a general bit. Whenever they bring an X, it means something that can change. P is X meters south of B. The engineers decide to drill from A to P and then from P to C. So they go from A to P and then they do that. So they go through the normal rock here and then through the hard rock. Through normal rock from A to P, the drill moves forward at 2 meters per hour. Through the hard rock from P to C, so this bit, it moves forward at 1 meter per hour. So you would expect that it goes slower through the harder rock, more challenging rock to get through. Explain why the time in hours t that it takes to drill the tunnel can be modelled by this equation. T equals 500 minus x over 2 plus the square root of 90,000 plus x squared. Right, so when it says time, you know there's a triangle for that. D's at the top, dst. So time equals distance over speed. We have distances that we can work out, and then we're going to have to use the speeds that we've just been given. So if we go back to the diagram here, well, this distance from A to P, well, the whole distance from A to B is 500, and then you've got this x from P to B that could move. So that leaves here, this distance must be 500 minus x. Okay, 500 minus x is that distance. Then, if you consider this bit here, well, that is the bit we've already worked out, really. So it's going to be, we've already worked out using a number that we were given, but now x can move. It's still going to be Pythagoras. So this here, PC squared, is going to be x squared plus 300 squared. So let's write that down. PC squared equals x squared plus 300 squared. So that means that if you look at what we're aiming at, well, the 90,000 is going to be 300 squared. You can check that on your calculator. But 3 times 3 is 9, and you've got 0000. And I can just write these the other way around, really. So PC is going to be the square root of, well, it's x squared plus 90,000, but because it wants it like that, I'm just going to switch them around. 90,000 plus x squared. So that's one distance, PC. The other distance I've just put on the diagram was AP, which was 500 minus x. AP equals 500 minus x. So we've got the speed equals distance over time. We've got the two distances. We've got the two speeds as well. Remember, it's through the hard rock, it goes at 1 meter per hour, and through the soft rock it goes at 2 meters per hour. So time is going to be, well, it's the distance 500 minus x through the normal rock. Remember, it does that first. 500 minus x over the speed through the normal rock, which is 2, plus, and then it's going to be square root of 90,000 plus x squared. Well, that's over the speed that it goes through the hard rock, which is 1 meter per hour, so over 1. And that's why it equals this that we want it to equal. And it's a bit confusing, as in when it says explain, I think we've got enough in there. I would much rather see some maths than actual words, really. But we've written about distance and speed. What you could do is do a bit of labeling. I guess you could say distance over speed plus distance over speed plus dist over speed. If you write that, it's an explanation, and I've run out of room anyway. All the measurements are accurate. Write down a practical reason why the time given by the model may be different from the actual time. So when it says a practical reason, it means just understanding the context of what this is about. Now, this is about drilling a tunnel through rock, right? So you'd get a lot of leeway on this. It's anything to do with the actual difficulties in drilling a massive hole through rock, rather than making it about maths itself. So the sample one in the mark scheme is maybe when the drill changes direction. So when you switch from normal rock to hard rock, maybe that you actually have to turn the machine around, something like that, or maybe a tea break or refilling the machine, anything like that really. So I'll put could lose time changing direction, but anything that the examiner perceives as relevant and it's about the situation, you will get a mark for that. And remember, they're instructed to be positive in the awarding of marks. On the diagram, sketch the graph of t against x. So it's an interesting scale. We've got a broken scale here. So we want to start t, or y min, at 400 and y max at 600. X min is going to be 0 and x max 500. The formula that we're going to put in is over here. So it's 500 minus x over 2 plus the square root of 90,000 plus x squared. So go to your graph, 500 minus x over 2. Over 2 plus the square root of 90,000 plus x squared. Okay, just like that. And I think I already set my view window, but just to check, oh no, it's not right. So x min 0, that's fine. X max 500. Y min, so we want a y min of where this broken scale starts. 400 is correct, and then y max of say 6. It needs to be 600. Okay, go back to it. And now it's an interesting graph, a bit of a curve. It might be useful to know what that point is, just for some communication. So if we just work out where that is, it looks like a y-intercept, but you could have done a trace there as well. So it's 550. So at 550, that's the point, and then it just sort of goes down and up again. So something like that would be fine. Find to the nearest meter the position of P, which gives the minimum time to drill the tunnel. So the minimum P, you're looking, it's this point that we're interested in there. And we can find that by going to GSolve, and we are looking for a minimum. And you can see that that happens when x is 173.205. I might just write that down, 173.205. The y value there is 509.808. Okay, so the minimum value of P, the position of P, we're looking for an x value. So it's when x is 173. Well, it's asking for meters from B, so it is the x that it wants. And it does say to the nearest meter, so 173. And then it says find the minimum time. Well, the time value is this here. It says correct to the nearest 10 hours. So to the nearest 10, this number is 510. To drill through normal rock costs $2,000 per hour. To drill through hard rock costs $3,000 per hour. The total cost of drilling the tunnel is $N,000. Write down a model for N in terms of X. Right, so we already have a model for the time, and it's already split into the time through the different types of rock. So if we just use these costs, and it's all per hour as well. This is $2,000 per hour. And if you look at the model in terms of time, this gives a time in hours, t in hours. And remember, this bit of the model is the normal rock, and this is the hard rock. So all we really need to do is take this number and times it by the cost per hour to drill through normal rock. And all we need to do is take this bit and times it by the cost per hour to drill through the hard rock. So that means N is going to be, well, it's 2 times the time that we spend drilling through normal rock. So that is 500 minus x over 2. 500 minus x over 2, we'll tidy it up in a minute, plus 3, so $3,000 per hour, times the amount of time we spend drilling through hard rock, which is the square root of 90,000 plus x squared. Plus x squared. So if you think about this, to tidy it up, well, the 2's are going to cancel. The 2 and 2, 1 and 1 will disappear those. So you're just going to have n equals 500 minus x plus, and then 3 times, or we'll just ditch the times sign, 3 square root 90,000 plus x squared. Find to the nearest meter the position of P which gives the minimum cost. So we're going to have to go back to our graph. I don't know if you're aware of this, but you see this bit select here. You can turn a function on and off like that. So we've got the option to have the cost function as a separate place, and you can turn one on and off. Or we could just go into this, which I think if it was you in an exam, you're probably more likely to just adjust the model. It's just that I know that I'm probably going to use this again because I've looked at question 5. So what I am going to do is put the cost model in y2, and I'm going to turn y1 off. So the cost model is 500 minus x plus 3 times the square root of 90,000 plus x squared. Okay, so I hit that. That one's turned on, and I'm just going to go to this and press select, so I turn the blue one off, but I'm going to use it later. So now if we draw, I'm going to have to adjust the window, view window. So I would imagine the x bits are probably okay, but we're certainly going to have to change the y. Let's go up to 1,000, see how it looks. Okay, let's go up to 1,500. And at some point we'll be able to see, there we go, we can just about see a curve. So actually I might go up a little bit further as well. I'm going to go up to 2,000. But yeah, if you do get to a graph and you can't see what you want, it is nearly always is the view window. So do just mess around with it till you get something. So there we go, there's a graph. Now we don't need to plot this, but we need to minimize again. So find to the nearest meter the position of P that gives the minimum cost. Now remember, this graph is cost against x, as in the distance. So it hasn't given us a lot of space to find any to show communication, which is a bit annoying because I would want to show that. So I still think I'm going to kind of draw a little, this was n against x, and I'm still going to draw a little curve like that, and I still really want to show where that point is, even though I haven't got a lot of room. I'm still going to attempt to do it. So I'm Shift G solve, and I'm looking for a minimum, and that tells me when x is 106, y is 1348 or 1349. Okay, so I've got some communication in there. It could prove handy later. So find to the nearest meter the position of P which gives the minimum cost. So to the nearest meter, remember that's x, and it's given in the same way it was before as meters from B. So if we go back here, meters from B is x here, so from B, how far? And that is to the nearest meter 106, and then it says write in full this minimum cost correct to the nearest $10,000. So remember the units of this were $1,000. So this number here is 1349. In fact, I might even write that out. So it is 1348.5 0.528137. So that's that many $1,000. So then if I times this number by 1,000, 1, 2, 3, well, your number is going to be 1,348,528.14. So that's, and then to the nearest $10,000, well, you've got ones, tens, hundreds, thousands, 10,000. So that's the digit I'm interested in. The 4, you look next door, and the 4 will the 4 will round up to a 5 because the 8 is bigger than 5 or bigger. So it's going to be 1350, and we've been asked for the amount in full. So then we need placeholders up to the end of the, well, up to the decimal point, the end of the ones. So 1, 2, 3, 4, and then we need 3 zeros there. 1, 2, 3. Position of B and C are fixed. Investigate the position of P, which gives the minimum time when A is more than 500 meters south of B. Right, so we're back to the time model again, and it's a very open question. Just a little refresher of what it is. So before, we had this situation where you've got P moving, and it's saying that it's between 500 and B. So, and what would happen if you think about it? You've got some kind of distance here that we might need to give a name to. You don't know, it might be 600, it might be 700, it might be 800. It could be like another unknown, it could be a distance D or something like that. But you need to think, well, what will change and what will stay the same? So remember, our model for time is t equals 500 minus x over 2 plus 90,000 plus x squared. Now, remember what that was? That was distance over speed, as in the distance that they go through normal rock over the speed that they go through normal rock, plus the distance that they go, the distance that they go through the hard rock over the speed, which was just 1 through the hard rock. So this was normal rock and hard rock. So we need to have a look at it and think what would change and what would stay the same. So where the model came from, whatever they do here, this distance from, we're still going to go to AP somewhere. You're still going to have a point where you stop going through normal rock and you go through hard rock. So if you think about this triangle here, well, this distance BC is still going to be 300. It tells us that B and C are fixed. So BC will always be 300. We're also going to have a moving x. So just because x can now be, it can be longer than 500, you're still going to have this distance x from here where point P is. Point P is going to be down here, but you're still going to have this x on this triangle. So this distance through the hard rock isn't going to change because it's still a right angled triangle with x on one side, albeit bigger, and 300 on the other. So the distance through hard rock is still going to be 90,000 plus x squared, the square root of that. So that won't change. What will change is the distance that you go through normal rock, because you're going to have, instead of 500, you might have a 600 or a 700. So what you could do is start to investigate like that. So if we just go back to the original model, I'll switch this one back on and just turn the cost model off. And then, well, what happens, say, if we just change the 500 to a 600? What happens there? That's a kind of investigating. So if we were, if this distance A, if A was 600 away from P, what would happen then? So let's have a look. And there's a graph like that. And if we do a G-solve and the minimum, that is the same number. So it's still X would be 173 meters south of B to minimize the time. What would happen if it was 700 meters away? So we'll draw it again. You can still see the same sort of shape, and that's the wrong bit. You can still see the same sort of shape. So if we then look for the minimum, it still happens when X is 173 meters away. So it looks like it doesn't make any difference, right? So the X value will stay the same. What we could do is just change this model. If we just rewrite this model a little bit, so T equals 500 minus X over 2. We could rewrite this bit into 500 over 2 minus X over 2 plus square root of 90,000 plus X squared. Now basically what happens is whenever we change the distance of point A, if once A gets bigger than 500 meters, so if A becomes 600, 700, 800, all that will change is this bit. And if you think about this as a graph, you can see that all this is doing is translating the thing up and down. So once we increase this thing, it's not actually going to have any horizontal effect. So basically the sum of all of that is that X will stay the same. The minimum time will still be achieved when X equals 173 meters. Okay, and there's a lot of things you could write, but basically if I just say this you could write vertical translation only, which already is a bit more than you need. We could have shown some investigation with the graphs, but there's not a lot of room. This would certainly be enough for the marks. If AB equals D meters, explain using part A why the minimum time in hours is T equals D over 2 plus K, where K equals 260, correct to 3 significant figures. Right, so using part A, we know that the minimum time happens when X is 173-ish, or I'll get the longer number, I need to put it on the calculator. When X is somewhere around 173, so let's okay, when X is 173.205, we know the minimum time happens. So also, we have done a little bit of work already when we were explaining why changing the point A doesn't actually affect the position of point P that achieves the minimum time. When we did this equation, this rewritten equation will actually be quite useful, because remember, think the 500 was D. We've been told, I'll just go back to the diagram, that AB is D. So this AB was the 500. Once it moves past 500, we're going to call it D. Remember, it's a moving length then. Right, so we can now substitute into this. So T equals, well, it's D over 2, that's this bit, minus X over 2. And remember, we're going to use the X value that gives the minimum time. And I'm just going to put 173.205 over 2 plus, well, it's plus the square root of 90,000 plus X squared, so 173.205 squared. Like that, get that one in. And hopefully all of this here will be very close to 260, and then we've got what we want. So if we go to the main bit of the calculator, minus 173.205 over 2 plus the square root of 90,000 plus 173.205 squared. And that is very useful. It comes out at 259.807. So T equals D over 2 plus 259.807. So when we're looking for this minimum time here, T equals D over 2 plus 260. That's 23SF.